Well, I'm going to talk about my dissertation. That is a bi-objetive multiperiod fuzzy scheduling for a multimodal urban transport system. The agenda we're going to follow, well, first I'm going to give a brief introduction of the problem. I will talk about fuzzy programming. Then I will explain about the modeling approach, the preprocessing we are using, and the methodology. And finally, I want to explain the experimental design. And I will some conclusions, and then we have a time for questions. Well, the urban transport planning process has four main activities: the network design, timetable development, vehicle scaling, and crew scaling. Each one of these activities has sub-activities, and the input or the output of one of these activities or sub-activities is the input for the next one. So we are working, or we will be working in the timetable development, which has frequencies and headways and timetable construction. That's the problem we are working on. Well, the problem being addressed here is about the integration of minimal frequency calculation and departure time assignment for the construction of urban transport timetables. Besides, this problem is hard because the computational time that we use to solve this problem, well, is huge, and we are proposing the model for multimodal transport system. We want to synchronize different kind of transport systems, and we have the objective problem. We want to minimize the cost and to maximize the synchronizations. And we are considering demand uncertainty. The main characteristics of our problem is the minimal frequency determination depends on headways definition. And we have a defined scaling horizon, and generally the planners divide or split that scaling horizon into smaller time periods, and in such that time periods the demand can be considered almost constant. We assume that we have more than one transportation mode, in each mode has its own regulations and structures and all that study requirements. Also, the demand is unknown, but it follows certain patterns, like the time of the day of the week, and the season of the year. We have transfer nodes. In those transfer nodes, passengers will transfer from one road to another, and for a transfer to occur, well, those roads needs to be synchronized. Also, we have bunching nodes, and on those bunching nodes is when a lot of buses or units of vehicles are bunching, and we should control that bunching. And finally, we have a fixed and a variable cost. The variable cost depends on the departures we assign, and also depends of the length of each road. And the fixed cost is just the administration cost of the organization. Well, in the literature review, we have that all the previous characteristics that I already mentioned, well, we have found that no one has handled or has worked with all of them in just one approach. That's why we are proposing to work in a multi-objective problem for multi-period synchronizations in a multimodal network with multiple activities, and also we are working with on-demand uncertainty. The motivation that for us to work with this problem well is that frequency and timetabling problems are problems that the decision makers face every day, and also the decision makers plan a scaling, and then they modify that scaling according to their experience. And every change that they do well affects the next activity of the transport process. And most companies in Mexico do not have a computerized system for the train tabling construction. That's one of our our most important motivations to work with this. To work with the demand uncertainty, well, we are working with fuzzy programming, and in a mixed integer linear problem, we have partial fuzzy or complete fuzzy. In a complete fuzzy is when all the constraints, all the parameters, and all the variables are fuzzy. And in a partial fuzzy, well, just one of the parameters of some constraints are considered fuzzy. In our model, we are working with a partial fuzzy model. Also, in fuzzy programming, we have fuzzy numbers like triangular fuzzy numbers or trapezoidal fuzzy numbers. We are considering triangular fuzzy numbers. And to compare those fuzzy numbers, we have different methods. The method we are using here is a K-preference method. And, well, why we decide to use fuzzy programming and not stochastic programming? Well, we think that it's easier for the decision maker to give a vague number or a fuzzy number related to the parameters we are working on, in this case, the demand. And the stochastic programming we know is modeled, and the uncertainty is modeled through the discrete or continuous probabilities function, and probably it will be more complicated to the decision makers. Well, it is common that an assignation of departures in the urban transport system obey, the original approach we followed to represent the departures follows some characteristics. We are considering as the decision variables the departures and the synchronizations. We know that we have found in the literature that even highways or even loads proposed by Seder work well for planners as guide to determine the quantity of departures. But in real life, we need more flexibility to determine the departures. So we split the time period into little intervals where the intervals are divided by the minimum headway. So instead of have a lot of variables or decision variables for determining the departure time, we were proposing this and it gives us a less number of variables. It is common in assignation of departures in a urban transport system obey certain policies. Among the most common, there are the first departure, the policy for the consecutive departures, and the policy for the last departure. Here we are working with a range of intervals. For the first departure, we said that the first departure has to depart between the first interval and the TC interval. The TC interval is the ratio between the maximum and the minimum headways. And also we have that the first departure has time to depart before the maximum headway. For two consecutive departures, we said that, well, at least those departures has to be separated by a minimum headway and at most by the maximum headway. And the range that we have is that they have to depart between the MCP and the MSP interval. That is, the MCP is the farthest interval where a departure can occur, and the MCP is the nearest interval where a departure can occur. For the last departure, we said that a decision maker, we are assuming that a decision maker says that, well, it has to be between the end of the period and the end of the period minus a fixed time by the decision maker. And this also is the same. We are proposing that if the last departure has to be between a range of intervals where Tm is the farthest interval where a departure can occur, and n interval is the last departure when the last departure can occur. Well, in our formulations, transfer synchronization is required at single node or at two closed nodes. That is the case of letter C. Um, in each synchronization, we have an origin and destination pair of rows, and also we have the time that the scaling period, and we have the synchronization that should take place. All those properties of a synchronization require at least 5 indexes, which in practice yields a huge amount of decision variables representing synchronization and related constraints. That is why it's very important to reduce the total number of variables representing synchronizations. Synchronizations at transfer nodes are directional. That means that if a synchronization occurs from one row to another and vice versa. Another preprocessing that we have is the determine which frequency method proposed by Seller in the literature we are going to use in each interval. And we're using the algorithm he proposed in 2007. First, we had to construct the load profiles for each period, and if that load profile is less or equal than 0.5, then we're going to use the method 3 and method 4. But the method 4, we're going to use it with different percentages, and we're going to maintain method 3 as a lower bound. And if the load profile is greater than 0.5, then we're going to use the method 1 or method 2, and we are going to use a chi-square test to determine which one of those methods we're going to use. In that algorithm to determine the frequency method, the parameters are deterministic, and as we are considering demand uncertain, we implemented or we modified that algorithm to incorporate the fuzzy parameters related to demand. Well, we defined for the synchronizations, we've made also a pre-processing step. We define the window time that allow to identify the pair of departures for two rows that should synchronize at a certain synchronization node. We are considering multi-period synchronization. Also, we are considering the possibility that a synchronization can occur between two different nodes or in a single node, and also the synchronization can occur between different transport modes. The procedure we are following is that for a given period, we select a synchronization node, and for each pair of rows that should synchronize, we identify the origin road and the destination road. And for each pair of origin and destination road, we determine the departures of each one of those rows that can synchronize in that period. But we are considering the departures of the previous periods. And for each departure of set of roads for the origin and for the destination road, we determine which departures can synchronize the transfer between both, considering the maximum transfer time between both nodes, the holding time, and the time that a unit remains in the node. In this way, we restrict more the set of variables that represent the possible synchronizations, as well as the constraint of synchronizations. And another preprocessing that we have is how to convert our fuzzy model to a crisp model. Well, as we said before, we are considering demand uncertainty. And the methods that Setter proposed is for deterministic data, so we needed to modify them to implement the uncertainty of the demand in those methods. The minimum frequency depends on the demand that we have. So in our model, the minimum frequency that has to be satisfied is between the maximum total number of departures, the frequency determined by those frequency methods proposed by Setter, or that we are considering as a lower bound, and a basic frequency calculated. Well, when we have a fuzzy model, we need to convert to a crisp model, and we are using the k-preference method. That means that if we have one fuzzy constraint, then we have, using this k-preference method, we will have two crisp constraints. And that's also a pre-processing that we do before to execute our model. The decision support process has the intelligence phase, the design phase, the selection phase. For the intelligence phase, we are proposing the mathematical model. For the design phase, we propose the optimization. And for the selection phase, the interactive method. We are just working here with these three phases, but the last phase of the decision support process is the implementation. For the design phase, we use the S-Aumicon method. There is a new derivation of the method epsilon constraint augmented. That S-Aumicon allows to generate all efficient solutions of the multi-objective problem. And also, when we have more than 3 objectives in our problem, it has acceleration algorithms that help us to reduce the execution time. Well, we generated 32 instances randomly, controlling certain parameters like rows, periods, nodes, density, and headways. The minimum rows are 8 and the maximum are 20. Then we have 2 periods as minimum and 12 as the maximum. 10 nodes for minimum and 115 as maximum. For density, with density I mean the number of nodes with synchronization. The synchronization nodes, that's what I mean with density. We have it as minimum 2 and as maximum 12. And for headways, we are considering a variation or a range between 5 and 10 as minimum and maximum, and 5 and 20 as minimum and maximum. The objective of our experimental design is to investigate the impact of those parameters in the instance complexity. We have a factorial design with 3 parameters, that is confidence level, demand level, and fuzziness of demand. The confidence level is the confidence that the decision maker has when he gives you a parameter, a range from a parameter. And the demand is just if we have low demand or high demand. And fuzziness is the range of variation of that fuzzy number. Well, each factor has a low and a high level, and every instance was executed for all combinations of those factors. We are using OPL to solve or to program our S-Aumicon. We solve it in a Unix server using Cplex 12.2. We gave an execution time of 3,600 seconds for compiling a solution. We are using domain reduction. We gave priority of variables and all the preprocessing I already mentioned. And well, the results that we have is that the parameter or the aspect of the instance that affects more in the execution time is the periods, and then is followed by the rows and the nodes. We have also the confidence level as a parameter, as a factor that affects more in the execution time. Then density, highways, and the level of demand, it's almost the same, but we found out that the fuzziness or the range of variation in a fuzzy number doesn't affect a lot in the executions of the instances. Also, we have found that the cost and synchronizations are practically independent. We think that is because right now we are just considering demand uncertainty, and we hope that when we consider also uncertainty of the travel time, well, we hope that also the synchronizations were going to affect in our problem. But the correlation between time, we have some correlation between time and cost. Well, as conclusions, we can say that we propose a mathematical model for the frequency and timetable integrated problem, considering demand uncertainty, and we are employing fuzzy programming. Well, these are some references, and I don't know if you have any questions. Well, Omar is asking that if my approach could be easily extended to consider fuzzy travel times. Yes, in fact, I already have the implementation, but I don't have results with travel times considering as fuzzy, but it's easily extended to fuzzy travel time. Mhm. Any comment or do you have any question? Well, someone is asking that if the what is the main advantage of the S omicron over the epsilon constraint algorithm? Well, with epsilon constraint algorithm, you probably obtain solutions that are not efficient, and with S omicron, you guarantee that all the solutions you are obtaining are efficient and not dominating solutions.
Okay, let's wait just 1 or 2 minutes to see if there is anyone that have any more questions. I find particularly interesting the model that you consider many elements that are not usually considered in literature, for example, the multiple planning periods and this fuzzy approach to model the uncertainty in passengers demand. And well, I have only one last question about the model. Usually, synchronization timetabling problems are complex to solve. Did you try to solve your model without the synchronization events? I mean, only focus on the frequency setting decisions just to see if the problem can be easily solved or not?
No, right now we have an experiment with that, but in a previous research we made we we started with this problem solving in a separate way, and we know that it's easier when we just focus on the frequency determination, but we want to integrate those activities because we consider it important in the planning process, and also because here in Mexico, there those problems the decision maker face every day to those problems, and they need to solve in an integrated way to avoid problems for the next activities of the planning process.